We've been talking about bonds as springs, and so far we've ignored the idea of the dipole moment. But the dipole moment is going to affect the intensity of the signal, and so we need to review it really quickly. And so if you have a dipole, if you have two charges separated, so two opposite charges separated, you could express the dipole moment as equal to the magnitude of charge in your dipole. So I'm going to write a lowercase delta here, our partial charge, times the distance between your charges d. So if you have a partial positive charge, right, separated by some distance by a partial negative charge, and if we're thinking about bonds as springs, I could draw a spring in here, right? So we have a magnitude of charge, one positive and one negative, so there's our magnitude of charge, separated by some distance d, and so obviously we're going to have a dipole moment, right? So we have a magnitude of charge separated by distance, so we get a dipole moment. If we get a stretching vibration, right? So if this bond stretches, if it stretches this way, we're obviously going to change the distance, and if we're changing the distance, we're changing the dipole moment. And that's important because only stretching vibrations that produce a change in the dipole moment are observed as signals on your IR spectrum. And so let's look at an example of this. Let's look at cyclohexanone. So here's cyclohexanone. We know that the carbonyl, right, has a dipole moment. The oxygen is more electronegative than the carbon, so the oxygen gets a partial negative. This carbon here gets a partial positive. And so we have a pretty large dipole moment associated with our carbonyl. And so we would expect to see a pretty strong signal for that carbonyl bond stretch. And if we look at our spectrum here and we go ahead and divide our diagnostic from our fingerprint region, right, here is a very, very strong signal. So just past 1700 wave numbers. This is approximately 1715, and this is in our double bond region that we talked about earlier. And so this must be the carbonyl bond stretch, right? So this represents, let me go ahead and use a different color. So this signal on our spectrum represents the carbonyl bond stretch, and this is a partial negative, partial positive. So large dipole moment means a strong signal. And if a large dipole moment means a strong signal, that means that a smaller dipole moment would be a weaker signal. So let's look at an example of that next. So we're going to compare these two IR spectra. And so now we're looking at a different molecule. We're looking at the IR spectrum for 1-hexene here. All right, once again, let's go ahead and divide our regions. Right, and if we look in the double bond region, right, we see this signal right here. And so if we drop down, the signal is about halfway between 1600 and 1700, so we'll say approximately 1650. So that's the signal in the double bond region, and of course that's the carbon-carbon double bond stretch. So that's this double bond here on 1-hexene. And notice that it's not as intense as the one that we talked about before, right? So this signal, let me go ahead and use a different color here. This signal is much stronger than this signal, right? So this is a weaker signal. So this must not have as strong of a dipole moment, and indeed that's the case. So if we think about this double bond right here, put some hydrogens on, so a little bit easier to think about. It's going to have a very small dipole moment. It has a dipole moment because this alkyl group right here. Remember, alkyl groups are electron donating, and so because it's not symmetric, you're going to get a weak dipole moment. And so because you have a weak dipole moment, you're not going to get an intense signal. You get this weaker signal here. So this, going back up here to this carbonyl again, this is really important when you're looking at IR spectrum. This super intense signal for a carbonyl often helps you figure out what functional groups that you're dealing with. All right, let's do one more. Let's compare this alkene to another alkene, right? So let's look at this one now. So over here we have 2,3-dimethyl-2-butene, right? So if we go 1, 2, 3, 4, that's 2,3-dimethyl-2-butene. And if we once again draw our line at around 1500 and we look in the double bond region, so somewhere in here, we don't see a signal. And the reason we don't see a signal is because this is a symmetrical alkene. Right, this is symmetric about the double bond here, so it's the same on both sides. And since it's a symmetrical alkene, there's no dipole moment, right? The electron donating effect of the alkyl groups would cancel. There's no dipole moment, and so therefore there's no change in dipole moment in dipole moment when the carbon-carbon double bond stretches, and so therefore we don't see a signal. And so this signal is absent on our IR spectrum. And so this is important to think about. If you have something that's symmetrical, right? You could be talking about an alkyne too. You're not going to see a signal on your IR spectrum. So that's something to think about.